Imagine a civilization so advanced, it can harness the entire energy output of its home star. This isn't just science fiction, it's a theoretical concept known as a Type II civilization on the Kardashev scale, a method of measuring a civilization's technological advancement based on the amount of energy it is able to use. A Type II civilization would be capable of feats of engineering that are almost unimaginable to us today, building structures on a scale that dwarfs entire planets. These colossal constructions, often called megastructures, are the hallmark of such an advanced society. One of the most famous and awe-inspiring of these megastructures is the Dyson Sphere. Proposed by physicist Freeman Dyson in 1960, it's a hypothetical shell built around a star to capture a massive percentage of its energy output. Instead of letting all that valuable stellar energy radiate uselessly into space, a Dyson sphere would collect it, providing a civilization with a virtually inexhaustible power source. This energy could fuel interstellar travel, power planetary-scale computations, or support a population numbering in the trillions. The concept sounds fantastical, but it's rooted in the logical progression of a civilization's energy needs. As a society expands and its technology becomes more complex, its demand for power grows exponentially. Eventually, the energy resources of a single planet, like geothermal, wind, or even nuclear fusion, would become insufficient. The next logical step would be to tap into the most powerful energy source in the solar system, the star itself. Building a true, solid shell around a star presents immense gravitational and material science challenges. A rigid sphere would not be gravitationally stable. Any slight nudge would cause parts of it to drift and eventually collide with the star or other parts of the sphere. Furthermore, the tensile strength required to prevent such a massive structure from collapsing under its own gravity is far beyond any material known to humankind. The sheer amount of material needed would also be staggering, likely requiring the disassembly of every planet, asteroid, and moon in the solar system. Because of these difficulties, a more plausible concept is a Dyson swarm. This isn't a solid shell but rather a massive collection of independent, orbiting solar collectors and habitats. Imagine billions or even trillions of satellites, each one a massive solar power station, all flying in tight, coordinated orbits around the star. They would collectively form a dense, cloud-like structure, effectively surrounding the star and capturing a significant portion of its light. This approach is far more practical from an engineering standpoint. Individual components could be constructed and launched over millennia, gradually adding to the swarm. Each habitat or collector would be an independent entity, capable of maneuvering to maintain its orbit and avoid collisions. This modular design also offers redundancy and scalability. If one satellite fails, it's a minor issue, not a catastrophic failure of the entire structure. The civilization could continue to expand the swarm as its energy needs grow, creating a constantly evolving megastructure. To build even a single element of a Dyson swarm would require physics and engineering far beyond our current capabilities. The primary challenge is obtaining the raw materials. A civilization would need to become masters of asteroid mining on an unprecedented scale. They would need to develop automated, self-replicating robotic systems that could travel throughout their solar system, identify resource-rich asteroids and planets, and process them into usable building materials. This process alone, dismantling entire celestial bodies, is a feat of Type II engineering. Once the materials are gathered, they must be launched into a precise orbit around the star. This would require incredibly efficient propulsion systems, perhaps powered by the very solar energy they are trying to collect. Techniques like mass drivers or space elevators could be used to lift materials from planetary surfaces into orbit without the use of chemical rockets. The logistics of coordinating the orbits of billions of individual swarm components would be a computational nightmare. An advanced artificial intelligence would be necessary to manage the entire system, preventing collisions, optimizing energy collection, and directing traffic within the swarm. Each satellite would need its own station-keeping thrusters and navigation systems to maintain a stable orbit. The gravitational interactions between all the swarm components and the central star would create a complex, chaotic system that requires constant, real-time adjustments. The energy collected by each satellite would then need to be transmitted efficiently. This might be done using focused microwave or laser beams, directing the power to where it's needed, whether that's a distant planet, an interstellar spacecraft, or another habitat within the swarm. In 2015, the Kepler Space Telescope detected something truly bizarre. It observed a star named KIC 846-2852, now famously known as Tabby's star, located nearly 1,500 light-years away from Earth. this star was exhibiting strange and dramatic dips in its brightness. Unlike the regular, predictable dimming caused by an orbiting planet, the light from Tabby's star was dropping by as much as 22% at irregular intervals. The pattern of dimming was chaotic and deep, suggesting that something very large and irregularly shaped was periodically blocking the star's light from our view. This was unlike anything astronomers had ever seen before. Naturally, the scientific community scrambled to find a natural explanation. Hypotheses ranged from a massive swarm of comets to the debris from a planetary collision. However, none of these explanations perfectly fit the observed data. The comet swarm theory, for instance, would require an unbelievable number of comets to cause such a significant dip in brightness, and the infrared signature expected from the dust warmed by the star was conspicuously absent. This lack of a clear natural explanation led some, including astronomer Jason Wright, to cautiously propose a more extraordinary possibility: an alien megastructure. The irregular dimming of Tabby's star was eerily consistent with what we might expect to see from a partially constructed Dyson swarm. A vast, incomplete cloud of orbiting collectors and habitats would block the starlight in just such a strange, aperiodic manner. This alien megastructure hypothesis captured the public's imagination and sparked a wave of excitement and speculation. Could we have stumbled upon the first evidence of a Type II civilization? The Search for Extraterrestrial Intelligence, SETI, Institute even pointed its radio telescopes at the star, listening for any artificial signals. Unfortunately, the search for signals came up empty. And as scientists continued to study Tabby's star, a more mundane explanation began to gain traction. Further observations, particularly in different wavelengths of light, suggested that the dimming was more likely caused by dust than by solid, opaque objects. The light was being filtered in a way that pointed towards fine dust particles rather than massive alien power stations. The leading theory now is that we are observing a massive cloud of circumstellar dust. The origin of this dust is still debated. It could be from shattered comets or the remnants of a destroyed planetoid. But the evidence leans away from an artificial structure. While Tabby's star may not be the home of a Dyson sphere, the search for such structures continues. The core idea behind finding them is to look for their waste heat. According to the laws of thermodynamics, any process that uses energy also generates waste heat. A Dyson sphere, while capturing visible light, would have to radiate its waste heat away to avoid overheating. This heat would be emitted as infrared radiation. Therefore, one way to search for Type II civilizations is to look for objects in the sky that are unusually bright in the infrared spectrum but have no corresponding visible star. Such a signature would be a telltale sign of a massive object completely shrouding a star and re-radiating its energy as heat. So far, searches of galaxy-wide infrared data have not yielded any definitive candidates. This could mean that Type II civilizations are incredibly rare, or perhaps they have found ways to manage their thermal emissions that we haven't considered. The concept of the Dyson sphere forces us to think about the ultimate limits of technology and the long-term future of life in the universe. It represents a level of mastery over the physical world that is, for now, purely theoretical. But every great technological leap began as a theoretical idea. From harnessing fire to splitting the atom, humanity has consistently pushed the boundaries of what is possible. The challenges of building a Dyson sphere are monumental, but they are matters of scale and engineering, not magic. Perhaps, in a distant future, our descendants will look back at our planetary civilization as a quaint, fledgling stage of development. They might live in orbiting habitats that are part of a growing swarm around our own sun, enjoying a level of energy and prosperity we can only dream of. Until then, the Dyson sphere remains a powerful symbol of ambition and a tantalizing possibility in our search for life beyond Earth. If you enjoyed this journey into the cosmos and want to explore more fascinating scientific concepts, be sure to subscribe to Curiosity Repo. We delve into the biggest questions of science and the universe,